Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 44 and this lecture's topic is cryogenic analog to digital converters. So, what we will do in this week's lectures is we will do a block level understanding of the readout circuitry which is there in a quantum computing system. Within that we first look at ADCs. In subsequent lectures we will be looking at oscillators, low noise amplifiers. We will be also looking at mixers and other maybe one digital block as well, for example mux or demux utility in a low temperature. So, the topic which we are going to deal with now is slightly deviating from devices to circuits, and in the circuits also we are going in the mixed signal domain to a larger extent. The reason for studying this analog to digital converter, the motivation behind this at cryogenic is something like this, that most of your signals which are coming from readout circuitry will be in analog domain and they need to be converted to a digital domain in order to do a computation for it, right, because all the computation is happening in the digital domain and therefore you require an analog to digital converter. To be kept in mind is that these converters are also sitting at extremely low temperatures where all the device phenomena which we have already discussed is under process, and therefore extracting the last bit from a converter is very difficult in case of a cryogenic CMOS inverter. So, we will be looking at the importance of obviously analog to digital converters, basic operation of ADC, challenges at cryo-CMOS, and then what is the requirement for cryogenic ADC, then look at the architecture of cryogenic ADC and then performance matrix of ADC. So, what are the performance matrix by which you will be actually saying that whether the particular ADC is cryogenic sort of it is able to pass all the tests for cryogenics. Now, low temperature, so where will you use it? One is in the computation process, quantum computing, but you can also use in many of the space applications where you require low temperature detectors, and especially for space applications, right, where you require to take a photograph or maybe infrared image of a very far off planet or a very far off body, and the signal is so low that you will require that the detector, the optical detector or IR detector should be at extremely low temperature in order to detect it noise free. So, they are used in to a larger extent in mid and far infrared imaging systems, and they are for most of the space exploration requirements. And similarly, particle physics, when you want to collect the data from the particle physics, they have to be also put in cryogenic temperature. Typically, this is the temperature which is kept typically for the cryogenic applications, right. Now, the analog output signal of a cryogenic front end, right, the analog. So, let me say I have this ADC here, right, let us assume this to be as an ADC. I am giving you the general block and then we will go one by one. So, I have this ADC where the analog signal of the cryogenic front end, right, is being fed into maybe room temperature ADC or cryogenic ADC. So, I can have two types of ADC, I can have a cryogenic ADC. Room temperature ADC is well researched and large amount of data is available, but for cryogenic ADC much is to be done, right, where the ADC has to sit on the chip very close to the qubit in case of quantum computing purposes. Now, generally the shielded cable, the cables which run interconnects and cables which run which give you the readout signals, they might run into several meters, right, and they may run into meters. When they run into meters, they suffer from noise and electromagnetic interference. So, they suffer from noise and electromagnetic interference because of such a large length of the interconnect lines and the cables which are drawn from there. And now, most commercial ADCs which we use in most practical purposes are pipeline ADCs. Just to keep in your mind, you might not know what is a pipeline ADC, but just ADCs are the most commercially viable options available to you for larger number of pictures. So, we will come to that later on. However, we can also go into the successive approximation register SAR ADC based design. Successive approximation register, also referred to as SAR ADC, is also used, right. So, we will just look into that to a larger extent later on. We will go step by step understanding it. Need not go into details, I have already discussed with you to a larger extent this slide, most of the basic slides I have understood. However, one important point is that the analog to digital conversion actually therefore is a sort of interface between the real world with the digital system. The digital system is where you will do the computation, the real world is more or so analog in nature, right. And therefore, the development of digital electronic systems will depend upon a reliable ADC or analog to digital converter, so that proper conversion of the analog signal to digital signal is possible without any compromise on the quality of the output digital signal, right. So, that is the importance of ADC. There are n number of now literature available where you can look into the analog to digital converters utility in modern electronics. So, let us look at the basic ADC and its operation. So, before we go to basic ADC and its operation, we have already discussed about the low leakage and therefore low power of any design at low temperature, typically at 77 K, and there are less amount of abnormalities available when you do ADC design. We also work with these ADC designs. Please understand, we do not require a very low technology node to understand the ADCs, right. Even a high technology node such as 90 will be sufficient to understand the various operations of ADC in a sense. Now, if you look at the various block diagrams of an ADC, then this is how you convert an analog signal into a basic digital signal, right. I have an analog signal here, right, and I want to convert to a digital signal. So, this is my analog signal, which is my input, right, and my final aim is to get a digital signal, which is basically my output. So, what you do is, so basically analog is what? Analog is something like this, right. So, you need to first of all do what is known as sampling and holding the signal. So, sample means you are sampling the signal in this manner, right, and then holding the value here so that exact value can be replicated in this manner, right. This can be replicated in this manner. So, corresponding to each one, I can have various modules being generated. So, if you look at the first block here, which is basically the sample block, there it is continuous in time and amplitude, right. It is both continuous in time as well as amplitude. When you sample it, it is continuous in amplitude, you see it is continuous in amplitude, but it is becoming discrete in time. So, this is omega t versus voltage. So, you see I have discretized it into smaller elements here. So, therefore, it is discrete in time, however, it is continuous in amplitude, right. Similarly, when you hold it, holding means, so let me show you how I can put you hold is, let us suppose this is there. So, this is one sample and this is one sample. So, when I reach to this value, it holds the value to this value, and then when it reaches the next sampling input, the amplitude again rises up. So, basically what happens is, I can show you using this. Let us say I have this and I have this. So, if I discretize it here, right. So, I will be sampling here, holding, sampling, again holding, sampling, again holding, and so on and so forth. So, you are able to discretize to an extent in time domain the values of the voltages at a particular point, which is the second point. So, this is basically sample and hold circuitry which you do, and therefore, the output of the hold will be discrete in time, however, it will be still continuous in amplitude. So, basically the sample and hold outputs will be basically discrete in time and continuous in amplitude. So, typically in all current mixed signal blocks we use switch capacitor networks to generate these signals. Then what we do is we try to quantize. When I say quantization, I primarily mean to say that for every discrete time I put a value there. So, now it is discrete not only in time domain, but it is discrete in amplitude domain also, which means that for every one single time stamp you have one amplitude stamp available to you. So, and there is no continuity in the amplitude signal, and therefore, quantizer actually makes discrete in time and discrete in amplitude. then you finally encode it. Encoder means you are finally converting that coded signal to a digital value. It is very simple and straightforward to give you an idea about. Say I have signal like this, right. I divide the first, so there are 1, 2, 3, 4, right. There are 4 bits, there are 4 sections available. Now I can show in a very layman language, I can show you what do we mean by quantization. Now if you want to quantize this into 3 bits, then 2 to the power 3 there will be 8 such available states. So starting from 0 0 0 to 1 1 1, right. Now if the variation is, say if the input AC voltage is from 0 to 1, then what you do is, this is 1 volt, then you divide 1 by 8. So when 0 0 0 will be 0, 0 0 1 will be 1 by 8, right. 0 1 0 will be equals to 2 by 8, then so on and so forth. Is it okay? And that way, so whenever I reach to a value of 2 by 4, which is 1 by 2 volt, I say that you can write down 0 1 0. In a very basic language, I am trying to explain to you how I am quantizing it. And therefore, the output will be discrete in time domain, and the amplitude will now be in binary form. Do not worry about amplitude, but more importantly the in time domain it will be discrete in nature, right. So typically we have 2 types of ADCs available. One is a direct ADC and as the indirect ADC. We will have 2 types of ADC. One is a flash ADC, which is basically an example of direct ADC, and we have a successive approximation ADC as well as a dual ADC. Okay. Now in most of the cryogenic design which you do, you try to, so if you plot basically, so let us look at the other operations of challenges which you will face. The first challenge is, as I discussed with you earlier also, that you will have a current profile which is something like this, right, and this is a low to high and high to low transitions which happens between the drain current and the drain to source voltages at cryogenic temperatures. There are large number of data available both using experimental as well as using BC model to extract the values of the various problem domain or various ideas which you get. You can do it very easily by extracting the value of current at each and every voltage, and when you know the current, you also know the output voltage, and if it falls below that critical value, a particular digital block is inserted in that particular case. Now the way, there have been large number of papers which has dealt with it, but primarily if you look at a conventional comparator. So basically you need to also look into the fact whether the input voltage is above a voltage or below a voltage. If it is above a voltage, we define this to be as 1, if it is below a voltage, we define this to be as a 0, and we use typically comparators for that. We will be looking into this later on. But primarily when you look into the, so the way the modeling is done in cryogenic is that you compare the cryogenic experimental data with simulation data, and you try to find out the relationship between the resistance, which is a function of VDS and VDS. So you know how the variation of resistance will take place. So you can, when you do an equivalent circuit model, you can actually remove that resistance by, you can remove that active device by a resistance. Now at 4 Kelvin the threshold voltage increases, right, we have seen this, and therefore because the overdrive becomes very small and you are not able to drive large amount of currents, and the threshold voltage shift therefore affects the comparator accuracy and the reference margins. I will explain to you what do I mean by that. Let us suppose your threshold voltage was initially 0.5, but it has now reduced to 0.2, which means that when the input signal is rising, then earlier the device was getting on when the input signal crossed 0.5, right. Now that it is increasing, now the current is rising even at 0.2. So which means that the level at which the current starts to flow in a device changes because of cryo, and that affects the switching threshold or the comparator accuracy. That introduces a sort of an offset also. Moreover, there is something known as ADC linearity, maybe I will talk about it later on, but however at this stage you should know what is linearity is all about. Linearity primarily means that for equal change in the analog voltage, you should get equal change in the digital logic, which I just showed to you in the previous cycle. You see, it is 0, 1 by 8, this is also, the difference is 1 by 8, this difference is also 1 by 8. Here also the difference is 0, 0, 1 to 1 mode. However, because of device mismatch, there is offset and therefore linearity is also compromised into a larger extent, right. So, these are the few challenges which you face when you do a cryogenic circuits. Now, power consumption is, of course, as I discussed with you, is the most important constraint at cryo circuit design. Why? Because you require, you are refrigerating, you are doing a refrigeration at very low temperature, and therefore your power budgets are very much restricted in a sense. Moreover, if you remember, your qubits are changing, right, and you require very high sampling speeds in the readout circuitry to get a real time flavor of the state of the qubit. And you want to do a real time processing, you need to increase the sampling speed. When you increase the sampling speed, it means that the analog signals are sampled at a much more densely, and therefore the switching capacitor sample and hold circuit has to work more faster. More faster means switching and charging and discharging will take faster, which means that the power dissipation will be also larger. So, the challenge or requirement is to make the front end design as invariant to threshold voltage shifts, right. Now, if you look at there are two sort of mechanisms or two as such variations are available here, and the difference here is that so initially the traditional way to approach this problem, which was done way earlier, was in many of the cases earlier about a decade or so, was to keep the ADC and the control system at 300 Kelvin, right, and there was a long wire which used to be gone from 400 Kelvin to 300 Kelvin. Now, since this wire was seeing a temperature gradient, there was a good amount of thermal noise being introduced into the ADC, and not only that, there was the signal integrity issue also coming into picture. Then people thought that why not therefore keep the ADC and the control system back into the 4 Kelvin box, right. The cost you pay for it is that your ADC is a very power hungry element, very highly power dissipative, and therefore the power budgets needs to be kept at a very strong pace. The advantage which you get is, since ADC is physically closer to the mixer and so on and so forth, the amount of the interconnect lengths can be drastically reduced, and therefore my signal integrity issues can be taken care of at cryogenic controls, and these are all at very low temperature. So, the whole thing is sitting around at 4 Kelvin or so, right. Now, let us look at the architecture of a cryogenic ADC. Looks complicated, but it is not too much complicated in a sense that is all about. So, there are three elements here primarily. I have these latched comparators. These are comparators, which is basically a 1-bit comparator. I have a preamplifier here, right, and then I have an n-bit DAC here, digital to analog comparator, digital to analog converter is there, right, and they are connected in series with respect to each other. This is basically a successive approximation ADC in a sense. So, let us look at the first here. So, let us suppose there are you have an input. So, I am basically trying to do a DAC and then ADC. So, the DAC will convert digital to analog signal, which is basically done here, right, and then subsequent comparator, and this output goes to a standard ADC in a sense, right, for the cryogenic ADC. Now, this is an n-bit DAC which you see, right, this is an n-bit DAC and this is an inverter here, and these are all exclusive OR gates, right, these are all exclusive OR gates. Remember, exclusive OR gates, if 0 0 or 1 1 is there, and if 0 1 or 1 0 is there, exclusive OR gate tells me the value this to be as 0 0 and this will be equals to 1 1, which means that if you look carefully here, if you look at this bit line here which is coming, so there one is input, right, this is my n-bit DAC, digital to analog input. I have a clock here which is phi 2 bar, I have a clock here phi 2 bar which is given here, and this is giving n-bit clock here, and these are repetitive. So, this is one block, this is another block, and so on and so forth. This is terminating at C and 2C. So, whenever you have a bit coming here, suppose this bit is 1, then this will be basically coming as 1, this will be 0, this will be 0, depending on the value of phi 2 bar, right, this upper one or the lower one will be either 1 or 0. So if the lower one is 0 and if the switch capacitor network which is connected here switches on, this capacitor gets charged by that voltage, right, and therefore the amount of charge collected on the capacitance is in direct proportional to the amount of switches which has got closed and the number of bits which has got transferred from the successive approximation register. So, the charge is in a sense an indicator of how much amount of what bits have actually come. So, if it is 0 0 0 0 all are 0, you will never get a charge on the capacitor. If it is all 1, you will get the maximum charge, and anywhere between them, the digital input, you will get the charge difference between the two together. Now, what you do is that, let us suppose phi 2 bar is high, and then this and this are closed. Let us suppose when these are closed, the total charge, the total voltage developed here reaches to this transmission gate in a sense. If this is high, then this transistor switches on, NMOS switches on, and depending on the value of, so phi 1 and phi 1 bar are mutually exclusive switches. So, if phi 1 is high, then what happens is that this switches on, voltage which is developed here at this particular point gets passed through this switch, through this network, and to this capacitor CC, right, because phi 2 bar is still low here, and this charge goes to this comparator, and if this charge is greater than or less than V bias P or V bias N, the output will be either 0 or 1. So, the whole idea is to compare the total charge with the input which is given as here as VDD, and based on that the output will be either high or low in a sense. So, as I discussed with you, you have a latched comparator, you have an externally available SAR, and the digital gates are implemented in the cascaded structure, and all these are at low temperature design is there, right. Now, the comparator uses a PMOS input stage, right. Now, why? Because as I discussed with you earlier also, PMOS are relatively stable to cryogenic temperatures than N-type semiconductors. We need to understand one important point, and that I was discussing in the first stage also. Let me just highlight that at this. So, you see you have these transistors here, right, this, right, and so on and so. Similarly, these two all are coming in pairs, right, and they have to be properly matched. If they are not properly matched, there will be an offset which will be coming into the system, right, and that will degrade the overall accuracy of the ADC in a sense. Now, let me just quickly go through these slides and show you what the architecture is all about. So, if you look at the differential, so this is one of the another cryogenic ADC architecture known as capacitive transimpedance amplifier, CTA is used. It is also used in the cryogenic amplifier. So, it is chosen for its low robustness and very low power consumption, and what they ensure is that in the pre-charge phase the NMOS are fully charged, right, they are in saturation. So, when they are saturation, they are behaving like current source. This is basically the signal which you give phi 1 bar, where you give it here, you see this is phi 1 bar, this is phi 2 bar, right, this is phi 1 bar, this is phi, and this is phi 1. So, these signals are sort of given in this case. When your phi 2 bar, phi 1 bar are high and phi, so when phi 2 bar, phi 1 bar and reset bar are all, so these two are high and this is low, then you get reset, right. When you get phi 2 bar high, phi 1 bar low and phi bar low, you get pre-charge, and when both are low and only your reset bar is high, you get amplification. So, there are three stages which the CTA works. One important point is your differential nonlinearity and integrable nonlinearity. Differential nonlinearity is a measure by how much the actual step size between two adjacent ADC codes deviates from the ideal step size. So, if you remember, as you move from say 0 0 0 to 0 0 1, LSB moves from 0 to 1, right, in a sense, and then so between 0 0 1 and 0 0 0 and 0 0 1, the step size should always remain the same, right. The output digital code which you are generating should always be the same, right, that is known as digital differential nonlinearity or nonlinearity, DNL. What is INL? INL measures how much actual transfer of the ADC deviates from the best fit straight line. So, if you plot analog versus say this is digital analog, I should ideally get a straight line, right, because for every value of analog my digital should be always like this. However, it becomes something like this or something like this, right, from the actual best fit line, then we define that to be as a INL error or integral nonlinearity error. Now, what comes to our rescue is that ADC does not show any stability, instability or hysteresis when cooled to approximately 4 Kelvin. and INL. So, typically INL should not exceed 1 LSB, right, and it has been seen that increases typically from 0.5 to 0.8 in a sense, and DNL increases 0.4 to 1.1 in a sense when you go to extremely low temperatures around millikelvin region. There is a degradation of course, but within the limits and works very fine across it. We define the final two important parameters. One is known as SNDR and is given by 10 log of P signal upon power of signal upon power of noise plus power of distortion. And there is an effective number of bits ENOB we say, and is given as SNDR, which you have calculated minus 1.6 upon 6.02. So, if you know the SNDR, that 1.76 to subtract from that and divide by 6, and you will get approximately the EMOB, which accurately an ADC digitizes the analog signal in the real world operation. Example, so you are told to determine the effective ENOB of an ADC which is operating at 20 Kelvin, right, if the measured SNDR is 64.3. So, what you do 64.3 minus 1.76 divided by 6 is the ideal value is 10 bits. So, the effective number of bits it can resolve is 10 bits, right. So, effective, so which means that the resolution is 2 to the power 10, you can actually have 2 to the power 10 sort of bits resolution can be done. With this, let me recapitulate what we did. We quickly finished off, we will not go into details of individual blocks to a larger extent, but give you a brief idea about analog to digital converter, what are the various blocks of ADC. Then we came to the fact that how ADC's functionality is maintained, right, and what are the various errors which happens in an ADC. So, these were the few things which we learned this year, and we applied all these things to cryogenic temperature, right, temperature. So, with this I think we enjoyed the lecture. Till we meet next time, goodbye.